Welcome back everyone. We were actually supposed to talk about convolution of continuous time signals in this class, but I thought before moving forward, we should actually solve a few exercise problems on Fourier series, so that the ideas we developed in our last class actually uh, become stronger, right? So we shall be solving a few problems. So I hope that this class will clear up a few doubts regarding Fourier series for different signals. And afterwards, in the next class, we shall talk about systems and how convolution actually can give you the output of a system when the system is excited with a certain input. Right? In any case, we shall talk about solving few problems, calculating the Fourier series for a few signals in this class. So I'm waiting for a few more people to join. Then we shall start today's class. And again, the first thing I should tell you about today's class is that this is going to be quite mathematical today, because we shall actually be solving quite a few integrals today, right? So yeah, be ready for that. Again, I shall be solving most of the problems, and you shall be letting me know if you encountered any problem, any issues while solving the problems, right? And we shall have a few demonstrations as usual. Yes, we shall actually start with the last homework problem I gave you. So don't worry about that. And there are a few things we need to clear up. But one thing I should tell you first, tell you in this regard, is that for this course, Signals and Systems, Fourier series isn't that much important compared to Fourier transform. So we shall actually emphasize on Fourier transform later on, right? Because that is going to be the most important portion of this subject, because most signals are not periodic in nature, and because of that, Fourier series do not really apply for most of the signals we encounter daily, right? So Fourier transform is actually applicable for those signals. So in fact, for our course, we use Fourier transform way more often than Fourier series. So actually, Fourier transform would be a more important topic for us. We shall emphasize more on that. But in this course, in this class, we shall be actually talking about finding the Fourier series for a few standard periodic signals. Right. In any case, the first thing you should be able to do is to mathematically express the signal, right? Mathematically express the signal before actually calculating the Fourier series, right? You should be able to mathematically describe the signal that we are actually going to calculate the Fourier series for, right? So, and if you are somehow unable to do that, then you can, of course, cannot be able to calculate the Fourier series, right? Because the Fourier series involves an integration with the signal itself, right? So unless you can mathematically somehow describe the signal, you cannot calculate the Fourier series. So that's one of the important aspects of this, right? So with that said, only few people have joined, I think, right? Right. So I shall not be wasting any more time. So let's start, right? I would expect more people to join later on. Anyway, so again, I shall not be moving fast in this class today, because I know personally that things can be pretty difficult to understand. So I shall keep things slow, and so that you can actually follow properly, right? And again, let me know if you encounter any issue during the class. So let's start with the signal we had as an exercise for our last class, right? So let me draw the signal first. Okay, let me make a simple drawing. So this is the first exercise problem we are going to solve today. So this signal was pretty simple, and let me draw only one full period of the signal. I shall be happy with that, right? Yeah, good afternoon to all of you. Yes, some of you are saying that you were unable to express the signal we gave you as an exercise in the last class mathematically, right? So we are going to start with that. So don't worry. So yeah, I've only drawn a small portion of the signal I gave you earlier, and let me give you the values once again. So this is 1, this is -1, and this is pi, this is minus pi, this is 0, of course this is time, and this is the signal. So our problem was to actually, so I think we are back again. So I shall wait for 2 more minutes to let all the people join back. Right. So this is one of the hassles of taking online classes, right? The intermittent network issues. Right. And I hope this works this time, right? Without interruption. Right. So let's start back, right? So we have this signal, right? Which is quite the last one we actually gave you, right? So again, before we can even proceed, before we can even start, we should look at the signal and see whether it actually satisfies the Dirichlet conditions, right? So first of all, this signal is bounded, so there is this signal is not jumping to infinity, right? So that's one of the conditions satisfied. Then this signal has finite number of finite discontinuities. Yes, this signal indeed has discontinuities at points of at time points 0, 2 pi, 4 pi, and -2 pi, -4 pi, and so on. And it has only finite number of maximas, and these maximas and minimas, and these maximas and minimas are finite, right? So all the three Dirichlet conditions are satisfied. So once we can ensure that, then by the sufficiency of the Dirichlet conditions, we understand that this signal must have a Fourier series expression, right? But before we can actually calculate the Fourier series expression, we should be able to express this signal mathematically. But some of you have told me already that almost all of you were unable to somehow express this mathematically, right? So we shall have to first try to express this mathematically, right? So that's going to be our initial goal here, right? So with that said, so this is our signal, right? Understandably pretty simple anyway. So, and with this signal, first of all, we have to be able to express this signal mathematically. So our goal is to express one full period of the signal, right? Namely, from this point to this point, right? We have to be able to express this signal from this point to this point. Now, understandably, this signal has two portions, right? So I have to express this signal in a piecewise manner. One would be from -pi to 0, and the other would be from 0 to pi, right? So with that said, let's think about how we express this signal, right? So think about this portion, right? Think about this portion. Here, this is one important point and this is another important point, right? There is no issue about that. So if you are able to somehow express, figure out what these points are, right? Then we will be able to find out the expression for this straight line, because this is indeed a straight line, right? Right? So since this is a straight line, we can easily calculate the straight line. So in terms of points, in terms of coordinates, okay, so this is the horizontal coordinate, ordinate abscissa, and this is the vertical coordinate or the ordinate. So what is the abscissa at this point? It's 0, right? Time is 0. And what is the amplitude? That's 1. So this point in terms of coordinates is 0, 1. And what about this point? What about this point? So abscissa is pi, which is the time here, and the magnitude is 0, which is the ordinate here. So this point is pi, 0. I don't think there is any issue with that, right? Similarly, what about this point? Understandably, this point is 0, -1. And what about this point? This point is minus pi, 0. Right? So now we have all the 4 points for expressing these two straight lines, right? These are two straight lines, right? So let's first express this straight line we are talking about. So this portion here, right? So with this portion, of course, we know that, of course, from your school level classes, you know that a straight line can be expressed simply straight line passing through 2 points. So this is the 2-point form of a straight line, is something like y minus y1 equal to y2 minus y1 by x2 minus x1 into x minus x1, right? So in order to express this straight line, you shall have to be using this expression, right? And that's quite simple, right? So for this portion, so when time is between say 0 and pi, so basically we are talking about this portion. Okay, this is a straight line, right? And this passes through this. So now, of course, for our convenience, y is not y is actually x, and x is actually time, right? The horizontal axis is time, and y-axis is basically the amplitude axis, right? So instead of writing this for our expression, we shall be writing x minus x1 equal to x2 minus x1 by t2 minus t1 into t minus t1. So that will be our expression for the straight line, right? Because in the horizontal axis we have time, and in the vertical axis we have amplitude, right? So with that said, of course, try to understand what I'm writing here. So I'm x minus x1. So let's consider this to be the first point, right? It's entirely up to us, because whatever you consider the first point, the other one is going to be the second point. So this is x1, this is x1, this is y1, this is x2, this is y2 for this regard, right? So with that said, so x minus x1, that will be 0. So yeah, x minus sorry, wait a second, hold on. So this is t1, this is x1, this is t2, this is x2, right? So with that said, I would have x minus x1, that's equal to 1, right, equal to x2 minus x1, so 0 minus 1 divided by t2 minus t1, so pi minus 0, multiplied by t minus t1. And what is t1? T1 is 0, right? This is t1. So I essentially have an expression for the for this portion of the signal, right? So if I simplify this further, what do I get? I get x minus 1 equal to minus 1 by pi into t, right? So as a matter of fact, what do I get? I get x equal to minus t by pi plus 1, right? So with that said, now we can say that this portion of the signal has an expression of this one, minus t by pi plus 1. So in a very similar fashion, we can also calculate the expression for this portion of the signal, right? So if you can anytime you can interrupt me and ask me a question if you don't understand something here. Again, for my convenience, I would consider this to be t1, this to be x1, and this to be t2, this to be x2, right? So that is going to be our expression. So for example, here my expression is again x minus x1. So what is x1? What is x1? So this one. So x minus 0 equal to x2 minus x1. So what is x2 minus x1? x2 minus x1 is minus 1 minus 0 divided by y2 minus y divided by t2 minus t1, like that. So t2 minus t1, so 0 minus of minus pi, and we have multiplied with t minus t1. What is t1? Plus pi. So right, so with that said, we have this expression. So here I have x equal to minus 1 by pi, right? Minus 1 by pi, and we have t plus pi, right? And if we simplify this slightly, we have x equal to minus t by pi minus 1, right? Right, all right. So we have two portions, and this is the definition. Again, the slope of the lines are identical. Of course, these two lines are parallel, right? This portion and this portion, these two lines are parallel, only they are shifted, right? So this is the expression for the signal between, so this is for t, this is for this, so minus pi for this, right? So now for that signal which you somehow couldn't express in the mathematical form, this is going to be the mathematical form. So xt for this signal will basically have two portions. So one can be expressed as minus t by pi minus 1 with this limit, and other would be minus t by pi plus 1 with this limit. And of course, there is a jump discontinuity at t equal to 0. But this is the mathematical expression for the signal I gave you earlier in the last class as an exercise problem. But do tell me if there is any issue with this. I will be holding on for 2 minutes here, but please let me know if there is any issue. We are having way too many network issues today. Right, so I think we are again back. Right, right. So we have described the signal, right? But let me solve it for you without any issue. So again, we know that the Fourier series expression for this signal would have some expression like that. So I would have a0 by 2 plus a summation like this. So we actually derived this in the last class, right? So we have an cos nt plus bn sine nt, right? So that will be the expression, right, for the signal. And with that said, we already right off the bat we know a few things about the signal, right? So actually, instead of solving everything, so we know as engineers we have to first try to figure out a few things. So I shall not be solving everything, but I am going to tell you a few properties of Fourier series in this regard. So this is the DC component, right? So right, DC component, also known as DC bias in a signal. So with that regard, look at this signal. Okay, this signal is evenly spaced about the horizontal axis, right? So the amount of the signals that appears on top of the time axis is the amount of the signal that also appears in the below the axis, right? Below the time axis. So if you take an average of the signal over any time period, the average value is going to be 0. This signal has no DC shift, right? This signal has no DC bias, DC component. So of course, if you integrate the signal over minus pi and pi and calculate the DC component, which this is how you calculate the DC component, which is given as A0, which is the DC component, which is corresponding to the DC component from minus pi to pi. And if you calculate the DC component like this, of course this is going to be 0, right? This is going to be 0 because this signal is evenly spaced. Okay, and on this period, if you sum up the area, okay, just take the integral, of course that's going to be 0. So the DC component is 0. I think all of you can, and those who are willing to calculate this integral for the DC component, okay, I welcome you to do that, because that's very trivial in this regard, right? With that said, let me calculate, let's calculate this portion, right? This calculate the components for the coefficients for cosine components, right? So those will be calculated as an. So an is the coefficient for the n radian per second cosinusoidal component, right? And that's given by 1 by pi integration from minus pi to pi xt cos nt dt, right? Right. With that said, if you put this expression here, okay, we would see something very interesting here. Okay, I am going to tell you this. Okay, so before we proceed, let's see this. Let's talk about something important. Let's talk about odd and even signals. Right. So so that we don't have to calculate everything always, right? So let's start with odd signals. Let's start with odd signals. Idea is xt is considered odd if x of minus t is equal to minus xt. So that is when xt is considered an odd signal, right? So now do tell me, when is the signal odd, right? So look at this portion. Let me give you an example, very simple example. Let me draw a very simple example and do tell me whether the signal is odd or not, right? So the example we are talking about here, that signal in particular looks like this. The signal we have been talking about looks like this, right? The signal in particular we are talking about looks like this, right? So with that said, we are saying a signal is considered odd if this condition is satisfied. So what is x of minus t? It's a time reflection. So recall one of our previous classes, this is the time reflection, right? This is the time reflection. So this is the reflection about the time axis, right? Right? And what about this? This is an amplitude reflection. So it's a reflection about the amplitude axis, right? So let me draw what we get after doing a time reflection. So from this we are doing a time reflection, say. So if we do a time reflection, so if we flip the signal about the vertical axis, so we do a time flip, okay, so you already know that if you do a time flip, so isn't this what we are going to see? If we do a time flip, do tell me if this is what we are going to see, right? Right? And this is x of minus t, right? So this is a time reflection. So on this signal, if I do a time reflection, this is what we get, right? So time reflection means reflecting this way, right? So reflecting like this, flipping like this, right? Time flip. Now let's calculate x of minus xt. How do I calculate minus xt? By doing a vertical flip, right? By doing a vertical flip. So let's do that and let's see what we get. So now with this signal we are doing something called a amplitude reflection. And how do I do an amplitude reflection? Of course, I take the top, pull it to the bottom, take the top, pull it to the bottom, and take the bottom, pull it to the top. Okay, so we do a reflection like this, amplitude reflection. So if I do that on the signal, what do I see? So amplitude reflection is kind of like this, right? I'm doing a reflection like that. Okay, doing this kind of a reflection, right? So with that said, if I do that, again I do encounter the same thing, right? Now this is minus xt. So now, as you might already have seen that this signal under time reflection and under amplitude reflection look the same, right? So doing a time reflection on this signal is identical to doing a amplitude reflection. Okay, in the regard that the appearance of the signal does not change, right? So these two are identical in nature. Looking identical in nature. So this expression is valid here, right? So if I do a time reflection on the signal, would be identical to doing an amplitude reflection on the signal. Okay, and when this is true, then the signal is considered an odd signal. So this is an odd signal, right? So I think that's understood, right? Okay. Again, we shall elaborate on this later on as needed, right? On as needed basis. So the signal we have been talking about is an odd signal, right? So this signal is an odd signal, right? And again, multiplying odd signals with even signals, we only get odd signals, right? So for example, here, look at this one for this integration. So we are going back to the integration. Let's go back. Okay, let's go back. Now, if I look at this integration, so an, which is 1 by pi, integration from minus pi to pi xt on cos nt dt. Look at the signals. So this signal that I gave you is an odd signal, right? And this signal, of course, this is a cosine, right? This is an even signal. We already know that, right? And what is an even signal? We shall discuss everything later on. So even signals, because x of minus t is going to be just xt, right? So doing a time reflection does not change the signal for an even signal, right? So yeah, we will see that. So of course, if we take a minus sign on everything, so like this. So for example, consider ft to be this, xt into cos of nt, right? So then f of minus t would be x of minus t cos of minus nt. Now understandably, we already know xt is an odd signal, so this is going to be minus of xt, and cosine is an even signal, so this is going to be cos nt, right? So this is going to be minus ft. So this entire thing itself is an odd signal, right? So this entire integrand is actually an odd expression, right? So, and the limits are from minus a to plus a, and from your school level mathematics, you already know that the result of this integration is 0. So instead of calculating everything, we can actually apply the properties we learned in our school, and we can proceed by not calculating anything. Okay, right? So we learn things so that we don't have to work hard, really. So that is the idea here. So right off the bat, we already know that the signal does not have any DC component, so A0 is 0. We also know that the signal does not have any cosinusoidal component, so A and are 0, right? So we already know that these two, right? So now of course the signal must have some sinusoidal components, otherwise yeah, the entire idea falls apart, right? So, and those components are expressed with Bn. What is Bn? Bn is the coefficient of the n radian per second sinusoidal component present in the signal. And how do I express that? I express that using this, from minus pi to pi xt sine nt dt. Right? Now recall that we expressed this signal in two portions, right? Yeah. So this was our expression for the signal, right? So we had one expression when t was between minus pi and 0. We had another expression when t was between 0 and pi, right? So with that said, we have to split this integral into two portions, right? Of course, one of the portion is going to be from minus pi to 0, and that's on xt sine nt dt, and the other portion will be from 0 to pi xt sine nt dt, right? So these are the two components in which we are actually splitting the signal. So right, so with that said, I am going to write 1 by pi here, and then look at the signal very carefully. Okay, look at the signal. What do I see really? So here in this portion, I'm integrating from minus pi to 0, and what is the signal? The signal is minus t by pi minus 1 into sine nt dt. And let me again go back. Yeah, some of you already know the correct answer, right? Let me again go back to see whether I'm writing it correctly. Yeah. So wait a second. Yeah, that was on minus sign. Yeah, and we have plus from 0 to integration from 0 to pi on minus t by pi plus 1 sine nt dt. So that's the entire integration, right? Yeah, we are going to do that. So don't worry. So we're going to simplify things further. Of course, simplification is one of the most important things that you're going to do. So right, so with this I can write 1 by pi, and this is going to be split into two portions, right? So let's split the entire integral. Okay, so we have from minus pi to 0, and we have minus t by pi sine nt dt, and then again we have minus, when we have, let's put a plus sign and I'll do that, minus pi to 0, we have minus 1 into sine nt dt. So we have split this portion, right? And we're writing plus, and we are going to now split this portion. So from 0 to pi we have minus t by pi sine nt dt, and then we have plus 0 to pi 1 into sine nt dt, right? So that is how the integration is split into two portions, right? So all the portions have been properly split. Now let's look very carefully at these. Okay, let's look very carefully at this portion and at this portion. Okay, so what do I really have? If I bring the minus sign outside and also bring the minus sign outside and bring these two portions together, what do I have? I have minus, and I have minus sign outside, so we are bringing these two portions together. So I have minus pi to 0, okay, t by pi sine nt dt, and from this we have 0 to pi t by pi sine nt dt, right? And look at these portions. Okay, we have to somehow calculate these portions separately. So these portions will stay as they are. So for example, let me just use the zoom here, and with that we shall have minus integration from minus pi to 0 sine nt dt and plus 0 to pi sine nt and dt. Right. So I think we have finished the splitting part, right? Right. So we have the integration in. Yeah. Right. So, and again, yes, one of you are correct that we since this is even, this signal is even, that integration we are doing is an even part, so we can actually take 2 outside and integrate from 0 to pi instead. Okay, we could do that. We could do that easily. But let's see things in a different manner. So here, of course, we have from 1 by pi, and we have this integration from minus. So now we have minus sign outside, and these two integrations can be coupled up. So I have from minus pi to 0, and then we have minus pi to 0, and then we have t by pi sine nt dt, and then we have 0 to pi and this. So these two can be coupled up and be written as from 0 minus pi to pi, and here we have from minus pi to 0 sine nt dt, and we have plus 0 to pi sine nt dt. Right. Now, yes, some of you said that okay, we could have simplified on the get-go, right? At the very beginning, we could have simplified this integration, and instead of working so hard to calculate everything, we could say this is an odd signal, this is an odd signal, two odd signals multiply into an even signal, and we could put the limit from 0 to pi. But that would have made things slightly more difficult, because now we have an easier situation. Look here, we kind of have an easier situation, right? We simplify things slightly further. So what do I have? We have a simple odd signal, right? So we have minus 1 by pi here. Now we have t into sine nt. So that's an odd signal, right? So this is an odd signal, this is an odd signal. So these two multiply into an even signal, right? So with that said, this integration can be made into 2 integration from 0 to pi, and I have t sine nt dt, and minus, with this said, look carefully at these integrations. We have minus from minus pi to 0 sine nt dt, and plus from 0 to pi sine nt dt, right? Right. So with this, with that said, what are we trying to calculate? We are trying to calculate an, which is from minus pi, so 1 by pi, from minus pi to pi xt sine nt dt, right? Right. And we could initially have considered the fact that this is an odd signal and this is an odd signal, so the entire thing is even, and for an even signal, if this entire expression is even, so we can take 2 outside and bring the limit into, so like this. So I would have 2 by pi, and now this will be 0 to pi, and I would have xt sine nt dt. We could have done that and would actually eventually encounter the same result. So I have 2 by pi in this in that regard. So, and with that said, I would have from 0 to pi, and then what about xt? Within that limit xt is given by minus t by pi, okay, plus 1, and then we have sine nt dt, right? Right. So we have so we basically are doing 2 integrations. So one of them is minus 2 by pi square integration from 0 to pi t into sine nt. Another is plus 2 by pi integration from 0 to pi sine nt dt. Right. Right. I think this is not that difficult to understand. So now do tell me if you understood up to this point. Yes. We will later on see, we will later on discuss this fact that this for this Fourier series expression, yeah, this is the DC component, this is the even component, and this is the odd component of the signal. So this is representative of the DC component, this is representative of the even component, and this is representative of the odd component of the signals. So we shall discuss those later on. Right. So we have this integration at our hand. Right. So do tell me if there is any issue with this. Right. There is no issue with this. Right. Right. So again, look at this integration. This integration, if you calculate this, this results into a finite value, right? And let's do this integration as well. So, right. So let's do this integration separately. So we have from 0 to pi on sine nt dt. So how much is this integration from 0 to pi on sine nt dt? How much is this? Right. So of course that's going to be minus cos nt divided by n, and I have 0 to pi here, right? Right. So okay, instead of calculating everything like that, let's simplify it further. Let's expand this further and let's do the calculation. So I have minus 2 by pi square. Right. Now I have a situation where I shall have to use integration by parts, right? So with that said, let me write down the entire expression what we see here. So for integration by parts, we have to choose the first function as such that it can be easily differentiated, and the second function as such that it can be easily integrated, right? So of course t can be easily differentiated, and after differentiation it actually reduces, right? After t after differentiation becomes 1. So t is going to be my first function. So t, and then we are going to use this integration on the second function. So sine nt dt. Okay, you already, all of you know the formula for integration by parts. And then we have a minus sign. Then we have an integration derivative of the first function. So ddt of the first function, which is t, and then again an integration, okay, on the second function sine t and dt, and then taking dt over everything, right? So that's how the integration by parts actually works in this regard, and the limits are going to be from 0 to pi, and we have 2 by pi integration from 0 to pi sine nt dt, right? So we have minus 2 by pi square, and we have this integration which is t, and this is of course, look carefully, this is t, and then we have cos, so we have a minus sign, of course that integration is minus cos, right? Minus cos nt by n, and we have a minus sign, and if we differentiate this, this becomes 1, and this becomes, so again minus cos, so I have a plus sign, so cos nt by n, I have a dt, right? So that's again one integration left over, and we have a plus 2 by pi integration from so let's do the integration here. So we have again limits are from 0 to pi, and here we have integration from 0 to pi again, so the integration is minus cos nt by n and 0 to pi, right? So with that said, if I do calculate this, it becomes 2 by pi square. And if I now again, we have to first simplify, I mean calculate everything, then go for a simplification. Cos nt by n plus, again, now for this the integration is sine nt, so I have basically have an n square here, so I have sine nt by n square, right? And the lower limit is 0, the upper limit is pi, and we have plus 2 by pi. So let's put a minus sign outside. We have 2 by pi cos nt by pi, right? And we have 0 to pi, right? So that's our bn, right? We are calculating bn, expression for bn. Now look at this portion, right? These are the limits we are going to put. We are going to put pi as the limit and 0 as the limit, right? Now look at this portion. This is sine nt, right? So if I put the lower limit, then becomes sine 0. That's a 0. If I put the upper limit, then becomes sine any integer multiple of pi. So this portion is irrespective of the value. This portion is 0, right? For the upper limit, this is also 0. For the lower limit, this is also 0, right? Because for the upper limit, this becomes sine n pi, and for any value of n, that is going to give me a 0, right? But that's not going to be true for everything else here. So let's see further, right? So let me simplify even further by putting the upper limits and lower limits, right? So now if I put the upper limit and lower limit, so I have minus 2 by pi square, okay? Now I'm putting the upper limit here, so I have minus t, and cos I have n pi divided by n. Now if I put the lower limit, of course I did already put the lower limit here. If I put the lower limit here, so if I put t equal to 0, then this portion becomes 0, because I have a t multiplied here, right? That portion becomes 0, so I have a minus 0. Done with the first portion. And what about the second portion? What about the second portion? So we have a minus 2 by pi, right? So if I now put the upper limit, I have, sorry, did I write a pi here? It's going to be n, right? Right. So if I put the upper limit here, so what do I get? I get cos n pi divided by n, and then lower limit, so cos 0, which is basically 1, so I have 1 by n. So that is what we see here, right? So sorry, I did not put the value of pi here, so that's going to be pi, right? That's going to be pi. Yes, right. So if I now simplify further and multiply everything, simplify further, so what do I see? I see that it's 2 by n pi, okay, 2 by n pi, so this minus signs cancel out, this one of the pi is cancel out, I have 2 by n pi cos n pi, then I have a minus 2 by n pi cos n pi, and then you have a plus 2 by n pi, right? So do tell me if there is any problem understanding this. Right? There is no issue about understanding this, right? So this is actually a very simple problem, because these two are actually cancelling out with each other, right? So these two are cancelling out with each other, so happily we have 2 by n pi. So as a matter of fact, this is easier than the problem we actually did in the last class, right? So we have, therefore we have bn is equal to 2 by n pi. So what did we see so far? Okay, let's go back again. In the Fourier series, again we shall discuss these things in elaborate details, so don't worry about anything. In the Fourier series, this portion represents the DC component of the signal, this portion represents the even components of the signal, and this portion represents odd components of the signal, right? So now with that said, this signal we are discussing here does not have any DC component, because it is evenly spaced above and below the time axis, right? So there is no DC component of the signal, and this signal is odd, so this signal does not have any even component. If this signal were even, in that case we shall shortly do an even signal. Okay, if this signal were even, in that case, under that scenario, okay, this would have been there, this would not. But under scenarios where the signal is neither even nor odd, the signal does have even components and will also have odd components, and under those scenarios all these coefficients will be there. But for our example here, the signal does not have any DC component, does not have any even components, right? It only has odd components, and so we only have bn's, right? And what are bn's? These are the coefficients of the sinusoidal components present in the signal, right? So now I can say the xt, the signal, is like b1 sine t plus b2 sine 2t plus b3 sine 3t plus and so on, right? And we already know that bn is 2 by n pi, right? So what is b1? It's 2 by pi. So I have 2 by pi sine t plus. What is b2? b2 is 2 by 2 pi. So 2 by 2 pi sine 2t plus. What is b3? 2 by 3 pi sine 3t plus and so on. And subsequently, if I take 2 by pi common, right? If I take 2 by pi common out of everything, I would have sine t, I would have 1 by 2 sine 2t plus 1 by 3 sine 3t and so on, right? So the signal we have been discussing so far, this signal has a Fourier series expansion of this, right? Expansion of this, right? I believe all of you understood, right? Right, please raise your hand and ask me a question here. So if you haven't understood it, right? So it took me 1 hour. It took us 1 hour to actually go through the entire problem, right? We shall solve 2 more and then we shall actually end our discussion today. Right. Right. So again, those who are mathematically inclined, this can be written as simply 2 by pi, then in a summation form as n equal to 1 to infinity, 1 by n sine nt, right? Because put n equal to 1, so we have sine nt, then put n equal to 2, we have sine 1 by 2 sine 2t and so on. So let's do one mathematically. I mean, let me show you it programmatically. Okay. So let me make the program right now. Right. So what are we plotting? We're actually plotting 2 by pi and a summation on n equal to 1 to, say for example, m. I cannot really go up to infinity, right, in reality. And t varies from, say for example, minus pi to pi. Let's plot points, so it's about 1000 points, and let's manipulate from let's manipulate from 1 to, say for example, 50 steps of 1. right? So again, this is just the original signal, right? And if I keep on adding components, look carefully what the signal looks like. If I keep on adding components, look carefully what is happening to the signal. This is giving you the signal we actually are discussing here, right? Right. So this is the Fourier series for the signal, right? Again, if you reduce this, you're adding more and more components, and like that. Right. So let's pull this back here. Right. So I believe we actually were able to understand this, right? So let's jump into the next problem. So please let me know if you actually understood everything here we discussed here. So jump into the next problem. Let's jump into the next problem. But before I can actually jump into the next problem, okay, let me introduce you to the next problem, because this is a very famous signal, right? We are going to see right now. Right. So this is our exercise 2 today. Okay, let me draw the signal first. So let me draw the signal. And all of you are quite familiar with this kind of signal, right? Let me show you. I don't know how well I will be able to draw, but I shall try my best. Right. So this is a pretty familiar signal, right? Right. So can anybody in the chat tell me what signal this is? Right. So this is a rectified sine wave, right? This is a rectified sine wave, and of course this is a rectified sine wave. Right. And what is the expression? The expression is simply mod of sine t. Right? Yeah, full rectified sine wave, right? And amplitude here is 1, right? But my question is, what is the period? Of course, this is a periodic signal, right? But question is, what is the period of this signal? What is the period of this signal? Is it 2 pi? Is it still 2 pi? What is the period of the signal? So, what is the period of the signal? Can anybody tell me? because if you don't understand this, you won't be able to work out the expression for this. So what is the period of this signal? My question is. The fundamental period. So can anybody tell me what is the fundamental period of this signal? Yeah. So the fundamental period of the fundamental period of sine t is 2 pi. But if I do a full wave rectification on it and mathematically put basically if I put a mod sign here, okay, if I do a full wave rectification, the period becomes pi. Of course, after every pi interval, the signal repeats itself, right? Right? So instead of now doing the integration from minus pi to plus pi, that would be wrong. If I do the integration from minus pi to plus pi, our expression would be wrong, because that is not a full period of the signal. That's twice the full period of a signal, right? So we have to now consider a full period about the origin, right? And what is the period? The period is pi. So now I have to split pi about the origin. So with that regard, I can now say that this is going to be one split of the period. So technically from minus pi by 2, so we shall have from minus pi by 2 to plus pi by 2. So that's going to be one complete period. So for us, this signal has a period of pi, not 2 pi. So far we have been talking about signals that are periodic with a fundamental period of 2 pi. Now we shall be talking about signals that can have any arbitrary period, right? Because in Fourier analysis, the signal does not need to be periodic with a period of 2 pi. It can have any arbitrary period. As long as it's periodic and it satisfies the Dirichlet conditions, the signal must have a Fourier series expression, right? So we shall have this. So let me then go back. So the fundamental period is pi. The fundamental period for this signal is pi, right? So that's understandable, right? So now let's go back and recap what we know about Fourier series. We know that we know this, right? We know that if a signal is periodic, so for example, if xt is periodic with a period of 2 pi and it satisfies the Dirichlet conditions, then we know that xt can be expressed as a0 by 2 plus summation n equal to 1 to infinity an sine nt plus bn cos nt, right? So we discussed all these things in the last class. But what is sine nt? Sine nt, so for example, at n equal to 1, what do I have? I have sine t. Then we have sine 2t. Then we have sine 3t, and so on. So this is the fundamental sinusoid present in the signal. Okay. Similarly, this is the fundamental. This is the fundamental cosinusoid, right? Right. So this is the fundamental sinusoid, right? This is the next overtone. This is the next overtone side. So with that said, what is the frequency of this signal? What is the period of the signal? This signal has a period of 2 pi. So in the Fourier series, the fundamental should match the period of the fundamental signal would match with the period of the signal for which we are calculating the Fourier series, right? So for fundamental signals that have a period of 2 pi, the fundamental sinusoids also have a period of 2 pi, right? Right. So what about the next signal? The next signal has a period of pi, right? So in regard, this signal has a period of 2 pi by 2. The next signal has a period of 2 pi by 3. So we're talking about periods, right? So what about the frequencies? This signal has a frequency of 1 radian per second. This signal has a frequency of 2 radian per second. This signal has a frequency of 3 radian per second, and so on, right? Now again, try to understand something very important here. We are saying that xt is a signal that is periodic with a period of 2 pi, and that is precisely the reason why the fundamental signal here and also here are periodic with a period of 2 pi, and everything else is just an overtone of that, right? So the fundamental signal, so this signal is periodic with a period of 2 pi, so this signal has a fundamental frequency of 1 radian per second. So the fundamental sinusoid present in this should also have a fundamental frequency of 1 radian per second, and the other signals would have 2 radian per second, 3 radian per second, and so on frequencies, right? So now with that said, if I change everything and say if xt is periodic with a period of, instead of being periodic with a period of 2 pi, instead if it is periodic with a period of 1 second, then what happens to the Fourier series expression? What happens to the Fourier series expression? If xt is a periodic signal with a period of 1 second, instead of being 2 pi second the period, okay, what if the signal is periodic with a period of this? Then we can say we have same thing, right? We have a DC component, and then we have the sinusoidal components, but the sinusoidal components will now be checking for signals that are periodic with a period of 1 second, then the period of signals periodic with a period of 1 by 2 second, then signals periodic with a period of 1 by 3 seconds, and so on, right? So here, instead of being 2 pi, the time is going to be 1, 1 by 2, 1 by 3, and so on, right? So we shall have an cos something plus bn sine something, such that, let me complete, ask your question, I shall answer your question. So, right, so I need to have sinusoids, for example, something like this, sine something, such that its period is 1 second, right? Then we should need to have something, multiply the signal with something that has a period of 1 by 2 second, right? Then we need to have something and multiply the signal with that something, so that it has a period of 1 by 3 second. That's how we calculate things, right? So that's how we figure out the 1 Hertz component here. So this is 1 Hertz component. That's how we figure out the 2 Hertz component present in the signal. That's how we figure out the 3 Hertz component present in the signal. Just like we figured out the 1 radian per second component, 2 radian per second component, 3 radian per second component, right? So this was the period, right? Eventually. So now what do I, and so on, right? So what do I need to have? So what is what is the thing that I need to put here in order to make this sinusoid periodic with a period of 1 second, right? Understandably, a pi, right? So if I put pi t, of course, that's going to give me a sinusoid of 1 second, period of 1 second. So if I say 2 pi t, now I would have a sinusoid of period of 1 by 2 second. Similarly, if I have 3 pi t, then I will have something like this. So the same expression will be here. Instead of nt, I would just have n pi t. I would have n pi t, right? In the previous expression, we had nt when the fundamental signal, when the signal was periodic with a period of 2 pi. Now, when the signal is now periodic with a period of 1 second, now we have n pi t. So what did we just do? We did do something called a time contraction, right? So we have multiplied something with t. So when we multiply something with t like that, it's a time contraction, and we contracted time by a factor of pi. So the signal that was periodic with a period of 2 pi, okay, that was repeating itself after every 2 pi period, is now actually repeating themselves after every 1 second, right? So that was a time contraction, right? So, oh, sorry, one more thing. That's going to be 2 pi, right? That's going to be 2 pi. That's going to be 4 pi, and that's going to be 6 pi, and so on. Okay, like that. So this is going to be pi into n into 2 pi, right? N into 2 pi, right? Right. Right. So with that said, say if xt is periodic with a period of 2t. Now here t is any generic value, right? T is not pi. Okay. Then the Fourier series expression here is going to be xt, which is a0 by 2 plus summation n equal to 1 to infinity an cos. Now of course we are going to have signals that are periodic with a period of 2t, and then periodic with a period of 2t by 2, periodic with a period of 2t by 3, and so on, right? That's going to be n into 2 pi by 2t and t plus bn sine n into 2 pi by 2t and t, and so on. Okay? So these sinusoids, so if I simplify this further, I have a0 by 2, so n equal to 1 to infinity, and I have an cos n pi by t into t plus bn sine n pi by t into t. Right? So what did we just do? We did a time scaling, right? We did a time scaling. So let me go back to the example we were actually doing earlier. Okay, in this expression, look at this one, right? In this expression, for example, if I do this kind of a time scaling here, so if I divide, instead of having nt, if I divide everything by pi, for example, so for example if I do a 2nt, for example, right? If I do something like that, look carefully what do I see. Look carefully what happened. So instead of being pi, so this point was at pi, right? At that point, right? Now instead of being at pi, this point is now at pi by 2, right? So this point is at pi by 2 now, right? So we did a time scaling on the signal. So the now period of the signal has become pi, right? Similarly, instead of saying 2 here, if I say pi here, now look carefully what happened. The fundamental is now periodic with a period of 2, right? This is the fundamental. Now if I expand everything, see, we are talking about a sawtooth wave that is periodic with a period of 2, because see, this passes through the point 1, right? Something like that. So please let me know if you understood what I just discussed here. Right, so let's go back. So actually trying to figure out the Fourier series for this signal, right? Right. So if you have any query, please ask. right? So let's proceed, right? So xt is something like this. Xt is something like this, right? So mathematically expressing this signal would require two portions here. For example, again, one for this between 0 and minus pi by 2, that's this portion, and from this portion, again we need to express like that. So for example, when this is the value of this is the time span, okay, here this is positive, right, originally, so this would be simply sine t, and this is going to be minus of sine t, because we already know that, right, because that's the property of modulus, right? If you have a negative expression, we already have a negative sign, so the negative becomes positive, and so on. So that's the expression here. But look carefully, what is the nature of the signal here, right? Look carefully, what is the nature of the signal? So if I say x of minus t, I would have, so let's do it here. If I say x of minus t, then I would have mod sine of minus t, and then if I do the expression, I would have minus sine t, and that's again mod of sine t, which is again xt, right? So this signal is even, right? This signal is even. So since this signal is even, it is not going to have any odd component present in it, right? It's going to have only the even components, right? And again, if you take an average value of the signal, you would see the signal does not appear below the time axis at all, right? So it's going to have an average value. So for this signal, I shall have a0 and I shall also have an, right? I shall not have any bn components, right? So this signal is going to be expressed like this, for so a0 by 2 and then summation n equal to 1 to infinity, and then I would have an cos n pi by t plus bn cos n pi by capital T into time, and sorry, this is sine, and like that, okay? And in this regard, in this example, the period is pi, right? The period is pi, right? So if the period is pi, of course, I have to divide accordingly, right? The period is pi. So please let me know if you understand this thing properly or not, right? So right, so if the period is given as 2t, then we have this expression. So here, with that said, this is going to be 2t, right? We're saying that. So yeah, that's going to be 2t. So that's the difference here, right? So here, instead of being 2t, instead of being 2 pi the period, here period is 2t, right? And 2t is pi here. So capital T is basically pi by 2. So all I have to do now is put this expression here. So with that said, if I put t equal to pi by 2 here, so what do I get? I get a0 by 2 plus summation n equal to 1 to infinity, and I have an cos, instead of t, if I write pi by 2, I would have, instead of t we are writing pi by 2, right? Because for this signal 2t equal to pi, that's the total time span for which we are calculating, right? So here, if I, instead of t, if I put pi by 2, I would get 2nt plus bn sine 2nt, and like that, right? And what about a0? A0 is, as usual, integration from 1 by pi, integration from now it's from minus t to plus t, on xt dt. For this particular example, since 2t is pi, this is going to be 1 by pi from minus pi by 2 to pi by 2. So this is an entire period of the signal, and this is xt dt. That's how we calculate a0, right? So let's calculate that. So of course this xt itself is an even signal, right? You already know that. So this can be written as this. So from 0 to pi by 2 on xt dt. And with that said, this is going to be 2 by pi integration from 0 to pi by 2. And what is xt within that limit? It's simply sine t dt, right? So if I do the integration here, it becomes 2 by pi integration from so on cos t, and the limits are from 0 to pi by 2, right? So now if I put the upper limit and lower limit, of course, that's going to be 2 by pi. If I put the upper limit is 0, minus minus plus, so we have a plus sign, and 0 1, so I have 2 by pi, right? So I have 2 by pi. It's not difficult to understand. So I have a0, so therefore a0 equal to 2 by pi. So what is the DC component in the signal? So the DC component is given by a0 by 2, and that's going to be 1 by pi, right? So now let's calculate the even components present in the signal. So the cosinusoidal components, the cosine components, right? So that's given by an, right? So what is an? An is 1 by pi integration from minus t to t. Here again we are not calculating from minus pi to pi, because the signal has a period from minus t to t, so period of 2t, right? So minus t to t, and again we have xt, and now we are checking for sinusoids that are periodic with period of 2t and 2t by 1, 2t by 2, and 2t by 3, and 2t by 4, and so on. So instead of that, I would simply have cos n pi by t, right, into t. So if this is 1, so look at the previous examples we actually did. We had nt, right? So why did we have nt? Because capital T was just pi. What was capital T? Half period, right? Because 2t was the period. If for a signal 2t is equal to 2 pi, okay, which means the signal is periodic with a period of 2 pi, the full period is 2 pi, then t is pi, and with that said, pi by pi would be 1. We would end up with the expression we have been dealing with long ago, right? And that's the expression here. There is nothing different, anywhere, right? So for this particular example, I know that t is pi by 2. So the integration is going to be from minus pi by 2 to plus pi by 2, and xt, and cos, again I know 2t is equal to pi, right? I know that for this particular signal. Since 2t is equal to pi, of course t is going to be pi by 2, so I would have 2nt dt for this particular example, right? And subsequently, if I see, so look at this one. This is an even signal. This is an even signal. So this is an even signal. This is also an even signal. So their product is also an even signal. So I can employ our expression for even signals, and this integration becomes from 0 to pi by 2, and now we have xt cos 2nt dt. If any one of you have any issue with this, please let me know. Ask your questions. Right. 2 by pi integration from 0 to pi by 2. And what do I have for xt? Xt is simply sine t, right? Xt is simply sine t, and we have cos 2nt dt, right? And this can be dealt with very easily. For example, I can write 1 by pi here, and integration from 0 to pi by 2. Bring that 2 inside. I have 2 sine t cos 2nt dt and ask you to recall a formula that you studied in your school level. That's 2 sine a cos b is simply sine a plus b plus sine a minus b, right? So right, so we are going to apply this formula, of course. Okay, and so our an, which is now 1 by pi integration from 0 to pi by 2 on this 2 sine t cos 2 nt dt, okay, can be written as 1 by pi integration from 0 to pi by 2. And now I can actually basically split everything like that. So I would have sine a plus b, so t plus 2nt, and then sine a minus b, so sine t minus 2nt, and everything with dt, right? So with that said, it's going to be 1 by pi, and look at this very carefully. So 0 to pi by 2, 0 to pi by 2, let me clean this up. So this is going to be 1 by pi integration from 0 to pi by 2, and I have sine of 1 plus 2n t, right? And then I have plus sine of, okay, 1 minus 2n t, and we have a dt here, right? So with that said, it's 1 by pi. So now let's do the integration here, right? Finally, so this is going to be minus cos 1 plus 2n t divided by 1 plus 2n, right? And then similarly minus cos 1 minus 2n t, of course there is a bracket here, right, divided by 1 minus 2n, and the limits are from 0 to pi by 2. So again, this class is going to be a very long derivation class, right? Calculating too many things, right? So now let's before we can actually put the limits, let's take care of a few things. So I have minus cos 2n plus 1 t divided by 2n plus 1, and here this minus sign can be taken inside on the denominator, and it becomes 2n minus 1 instead of 1 minus 2n. And since cos is in the even function, I can put a minus sign inside without harming anything, and I can write cos 2n minus 1 into t, right? And subsequently the limits are from 0 to pi by 2 as usual, right? Right, there is no problem with that, right? So I have 1 by pi. Now let's put the upper limits and the lower limits, right? 1 by pi. So if I put the upper limit here, so what do I get? Minus cos 2n plus 1 into pi by 2 divided by 2n plus 1, and cos 2n minus 1 into pi by 2 divided by 2n minus 1, and then again we have let's not close the bracket. And for the lower limit, I would have a minus sign along with this minus, so minus, and again this minus. So if I put the 0 here, so this becomes 1, cos 0 is 1, so I would have minus 1 by 2n plus 1 and plus 1 by 2n minus 1. So now do tell me if you have understood this. Right. So with that said, it's 1 by pi, and look at this expression. Okay, we're trying to simplify things, so let me just write everything out, because cos, this is 2n plus 1 into pi by 2 divided by 2n plus 1, and I'm bringing this 2n plus 1 right next to this, so this is going to be plus 1 by 2n plus 1, and then we have a cos 2n minus 1 into pi by 2 divided by 2n minus 1, and we are bringing this minus 2n minus 1 right next to this. Right, so we have something like this. Right. Okay, repeat the last part means are you talking about this? So I'm putting the limits, right? So putting the upper limits and lower limits, right? There shouldn't be any issue about that. So I just put pi by 2 here and put 0 here. We just split everything. So we are bringing portions where bringing fractions where the denominator is n by 2n plus 1 and where the denominators are 2n minus 1 together, right? So we are bringing these two fractions together and these two fractions together. Okay, and there is nothing apart from that, right? And here, when I said when I talked about changing the values here, look at the minus sign here. If I bring the minus sign in the denominator, 1 minus 2n simply becomes 2n minus 1. And since this is an even function, I can always put a minus sign inside without changing anything outside, because that's how an even function works, right? And if I put the minus sign inside, what do I get? I get 2n minus 1. So instead of writing 1 minus 2n, I can just write, because simply we know cos theta is simply cos of minus theta, same thing. Because of that, we actually have got this, right? I think I answered your question, right? So with that said, we have an expression, enormous expression like that, right? But as engineers, we always should be able to simplify things as far as practicable. So look at this one very carefully. Okay, and if I bring 1 minus 2n plus 1 common, okay, what do I get? I get 1 minus cos 2n plus 1 into pi by 2, right? That's for the first one. And similarly for the next one, if I bring 1 by 2n minus 1 common, I would have let's deal with this way. Let's put a minus sign here. Okay, so I would have 1 minus cos 2n minus 1 pi by 2. Right. Right. So now let's find a pattern on this. Okay, we need to be able to find a pattern on this, because this is the end of the problem, for example. Okay, right? Because if you calculate an, for example, let me just go further. Okay, and what about bn? For example, if I calculate bn, we know that's going to be 1 by pi integration from minus t to t on xt, okay, sine n pi by capital T into t dt, just like the previous one, because this signal is expanded upon a period of span of 2t, right? So for example, that would be in this regard from minus pi by 2 to pi by 2 xt and sine 2nt, because capital T is pi by 2, and dt. But now in this regard, you can know that this signal is even, this is odd, so this entire thing is odd, so this integration is 0, right? So all the bn values are 0, right? Only the even components are there, right? So this is there, right? So this is the even component, and that is the only thing that is there. So let me just copy paste everything here. Right, so this is the even components, right? An, right? So let's try to figure out a pattern in this, right? So let me ask you this: what is the value of an? A1. So let's put n equal to 1, and what is the value of a1? And try to figure something very important out here. Okay, try to see that this 2n plus 1, for whatever integer value of n, this 2n plus 1 is always going to be an odd number, right? This 2n plus 1 is always going to be an odd number. This is never going to be an even number, right? So this is always going to be an odd number. So with that said, what is a1? A1 is 1 by pi, and you can use your calculator if you so desire, right? So when n is equal to 1, I have 1 by, what do I have here? 1 by 3, right? 1 by 3. When n is equal to 1, I have 1 by 3 here. I have 1 minus cos. When I have n equal to 1, I have 3 pi by 2, right? And then I have a minus. So n equal to 1, so that's 1, right? And I have 1 minus cos, so that's pi by 2, right? So now tell me, what is this? What is cos pi by 2? What is cos pi by 2? So all of you know cos pi by 2 is 0, right? Cos pi by 2 is 0. What is cos 3 pi by 2? What is the value of cos 3 pi by 2? The value of cos pi by 2 is 0, right? What is the value of cos 3 pi by 2? That's also 0. So what do I have? So I have 1 by pi into 1 by 3 into 1 minus 1. So what do I get? So I get minus 2 pi. So I get minus 2 by 3 pi. So that's our value for a1, right? Why do you think it's yeah, those two values are 0, right? So these two are 0, so subsequently I have this, right? Question: what is a2? What is a2? Again, look at this, okay, and with that a2 would be 1 by pi, and same thing. So I have here 1 by 2n plus 1. So when n is equal to 2, that's going to be 1 by 5, right? And it's going to be 1 minus cos 2n plus 1 pi by 2. So it's 5 pi by 2, right? And a minus 1 by 3, because n is equal to 2 now. When n is equal to 2, this is 4 minus 3, 4 minus 1, so that's 3. And this is going to be 1 minus cos 3 pi by 2, right? Right? So again and again we see that this is going to be 0. This is also going to be 0, right? So because these are all odd multiples of pi by 2, right? So for cosine, we know, so we know this cos, okay, 2n plus, so cos any odd number into pi by 2, that's a 0, right? We know that for sure. But these numbers are always going to be odd, right? So I now know that this is always going to be 0 no matter what, and this is also always going to be 0 no matter what, because these are odd multiples of pi by 2 on cosines, right? So instead of calculating everything like that, we can say, happily say, that an can be further simplified to something like this, 1 by pi. So I have 1 by pi, and this portion is 0, so I have 1 by 2n plus 1 minus 1 by 2n minus 1. Right? That's a very simplified expression for an. Right? So with that said, we can very easily now recalculate everything. So let's simplify this a slightly more, if you think that's a good idea. Okay. So in any case, that's 1 by pi, and it's 2n plus 1, it's 2n minus 1, it's 2n minus 1 minus 2n plus 1, and that simplifies to 1 by pi, okay, into 2n plus 1, 2n minus 1, and this is going to be minus 2. So I have minus 2 by pi, okay, minus 2 by pi into 1 by 2n minus 1, 2n plus 1. So those are the cosinusoidal components, right? So if you recall, A0 turned out to be, what did we calculate A0? Yeah, A0 turned out to be 1 by pi, right? So the DC component was, so A0 turned out to be 2 by pi, so A0 by 2 was 1 by pi. So A0 was 2 by pi, and AN turned out to be minus 2 by pi into 1 by 2n minus 1 into 2n plus 1, and Bn, all Bn's are 0, right? Right. So you can just keep on putting values for n, and subsequently we shall get all the coefficients, right? So we already calculate the value of A1. A1 would be minus 2 by pi into 1 by 1 into 3, right? That's minus 2 by pi into 1 by 3. What is A2? A2 is minus 2 by pi into, so this is going to be 5, and this is going to be 3. So this is going to be 5, and this is going to be 3, right? Yeah, 3. So rather I would say 3 into 5. 3 into 5. So minus 2 by pi into 1 by 15, right? Was that the thing we calculated? Yeah, yeah, right. So similarly, what is A3? It's going to be minus 2 by pi, and this is going to be 5 into 7 equal to minus 2 by pi into 1 by 35, and so on, right? 35 and so on, right? So I can say now that the signal looks like this: xt equal to A0 by 2. Again, A0 is 2 by pi, so this is 1 by pi. Then what is the coefficient of the fundamental cosinusoidal component? This is minus 2 by pi into 1 by 3. So this is minus 2 by pi into 1 by 3. But what is the fundamental cosinusoidal component? This is no longer cos t. Okay, this is no longer cos t. Look here. Look at this one, the expression originally. Okay, this is no longer cos t, but instead this is cos pi by capital T into t, right? That's the fundamental cosinusoidal component, right? So now this is going to be cos 2t, right? That is how things are going to work here, right? Because t was pi by 2. So this is going to be cos 2t. Because the fundamental period of the signal is pi instead of being 2 pi. So this signal should also, the fundamental signal should also have the same period as the original signal. So this signal also has a period of pi instead of 2 pi. Because the signal for which we are trying to calculate the Fourier series has a period of pi instead of 2 pi. So the fundamental signal present in here should also have a period of pi instead of 2 pi, right? Right. So the next harmonic here has an amplitude of minus 2 by pi into 1 by 15. So that's going to be minus 2 by 5, 2 by pi into 1 by 15, and that's going to be cos. Okay, that's next frequency. So to multiply this with 2, so I would have 4t. What is the amplitude of the next? That's going to be minus 2 by pi, that's a3, right, into 1 by 35. And what is the frequency? That is going to be 3 times of this one. That's going to be cos 60, and so on, right? But instead of writing things like that, we can always express it simply as a summation, right? So that's going to be 1 by pi, and minus, we can take 2 by pi common out of everything and put a summation sign and write n equal to 1 to infinity. Okay, right? So we have this 1 by 3, we have 1 by 15, we have 1 by 35. Where did these things come from? This thing simply came from this, right? 1 by 2 minus 1 by 2 minus 2n minus 1 into 2n plus 1 from that. So this is 3 into 5, so 15, 5 into 7, so 35, and so on. So that's going to be 1 by 2n minus 1 into 2n plus 1, and on top I have cos 2n t. In fact, this is cos 2 into pi, so cos n into pi by capital T into t, right? That is what it is, right? But in this example, in this question, for this particular signal, capital T is such that capital 2t is pi, so that's the whole period, right? So capital T is pi by 2. Again, I am emphasizing on this thing. So right, so instead of capital T, if you put pi by 2, you would get the final expression for the Fourier series. For example, n equal to 1 to infinity. So I have cos 2nt, that 2 is coming from this pi by 2, pi by t, and I have 2n plus 1 into 2n minus 1 into 2n plus 1, right? So that's the Fourier series for the rectified sinusoid for that particular example. Full wave rectified sinusoid. Right. So with that said, let me go back to the program and let me develop one for such. What am I doing? Yeah, manipulate, plot. Okay, so what am I going to plot? Yeah, let's okay, this is 1 by pi. Of course, remembering this is very difficult, right? Divide, escape pi, 1 by pi minus, what do I have in here? I have 2 by pi, I have 2 by escape pi, and we have a summation from n equal to 1 to whatever value I want, and I have a division here. On top I would have sine 2nt, and on the denominator I shall have 2n nt. On the denominator I shall have 2n minus 1 into 2n plus 1. Okay, and here afterwards I would say time is from, so for example, let's take a few cycles from minus 2 escape pi. So I'm plotting it from minus pi to pi, and let's consider, for example, up to 50. So from 1 to 50, steps of 1. Right. So look at this signal. Right. So that's the fundamental here. Again, this fundamental is periodic with a period of pi instead of 2 pi. Now if I keep on adding additional components, look carefully what is happening. If I keep on adding additional components, what is happening? Did it calculate properly? Oh. Yeah, that's going to be cos, not sine, right? Right. So now, say I'm adding extra components. Look carefully what is happening. This is approaching. See, that is the fundamental, right? Fundamental sinusoid here. Let me just change the period slightly back here, so that you have a better view of this. So that's the fundamental sinusoid, right? Now if I add on, so that's the cosinusoidal component, right? Fundamental. So if I add on more components, see, the signal is becoming flatter somehow. Look carefully, and the lower portion is becoming sharper and sharper. And eventually, if I add too many components, it looks like a pure rectified sine wave, right? Yeah. Now we have a full wave rectification, right? This is the fundamental component in a full wave rectified sine wave, but this is a full wave rectified sine wave. Right? As you can see, this signal is periodic with a period of pi, because after every pi, so this is pi, right? So after every pi interval, the signal repeats itself, right? So we took the signal from minus pi, by calculated everything from minus pi by 2 to plus pi by 2, right? So now let me end the discussion here today with an engineering problem, typical. Okay, so that you can actually tell. So instead of calculating everything again once more, so my question is this. Okay, what is the Fourier series for full wave rectified? Okay, after rectification we often do filtering, okay, to smooth the signals. We're not doing that, we're just doing a full wave rectification with diodes. Imagine, ideal diodes. Imagine full wave rectified sine wave of 50 Hertz. Imagine we are actually taking our line power, okay, and rectifying it, doing a full wave rectification. What is going to be the Fourier series for that? Okay, of course the Fourier series will be like this, but with slight modification, right? Fourier rectified. So for example, full wave rectified sine wave of 50 Hertz and say 230 volts. Right. So we have this signal 230 volts, 50 Hertz. So what is going to be the expression for the Fourier series for that? Typical or line level supply. So instead of calculating everything, because we already have an expression for this, right? So do tell me. So I shall have to first copy this, because we are going to use this here. So I'm asking you, what is the Fourier series for a full wave rectified sine wave of 50 Hertz, right? So I have this, right? Because I shall have to actually modify this expression. anyway, right? So instead of xt, I'm saying this is a full wave rectified Vt. So full wave rectified voltage waveform, right? So what? Please do tell me, what is the first thing we should take care of? What is the first thing we should take care of here? So this is the expression for the Fourier series for a full wave rectified sine wave for which the period is pi, right? Yeah, we have to change the frequency, but we also have to take care of the amplitude, right? So what do? I have to multiply the amplitude, right? Because in this example, we took a sinusoid. For example, let's go back, right? So this sinusoid has a peak amplitude of 1, right? Yeah, we have to change the, yes, we have to take care of the time period and the amplitude. Look carefully. This sinusoid had an amplitude of 1, right? This sinusoid had an amplitude of 1, peak amplitude of 1. So just have to multiply the amplitude here, right? So multiply the amplitude. So what is the amplitude here? If you say 230, it's wrong, because 230 is the RMS value, right? And for sinusoids, you know the relationship between peak and RMS. So the peak would be 230 into root 2. So we have to multiply everything with that first, because that takes me from 0 to, from a peak amplitude of 1 to a peak amplitude of 230 root 2, right? Because that's going to be the amplitude modification here we need, right? I think that's understood, right? And then we have to do a time modification here. So 50 Hertz, right? So 50 Hertz. When after doing a full wave rectification, the signal becomes 100 Hertz. Try to understand. Okay. So whenever you are doing a full wave rectification, the frequency doubles automatically, right? Right? The time period halves, right? So what is the 2t for this rectified wave? So after rectification, so I can say after rectification, frequency becomes 100 Hertz, right? So what is one full time period of this 100 Hertz signal? So if the signal is 100 Hertz, so what is one full time period for the signal? What is one full time period? Yeah, if 100 Hertz is the frequency, what is one full time period? For a 100 Hertz signal, how long does it take for the signal to repeat itself once? That's 1 by 100, right? 1 by 100 second. That's 1 by 100 seconds, right? So for me, capital T would be 1 by 200, right? So 1 by 200. Understand? Right. This signal is 100 Hertz, right? So it repeats itself after every 1 by 100 seconds, right? That's the whole period, which is represented by 2t in our expression. So t would be 1 by 200, right? 1 by 200. Since capital T is 1 by 200, we can now say that this capital T is going to be replaced by 1 by 200. So if you put 1 by 200 in that, we will get the expression. So this is going to be V RMS into root 2, like that. So with that said, the expression would be 230 root 2, okay, and then we have 1 by pi, then we have minus 2 by pi and a summation on n equal to 1 to infinity, and we have 2n minus 1 into 2n plus 1, and on top, instead of t, I would have 1 by 200. So that's going to be cosine, so that's going to be 1 by 200. So there's going to be 200 n pi t. 200 n pi t, right? So that's the expression, Fourier series expression for a full wave rectified 230 volt peak to peak, 230 volt RMS. So this is the Fourier series for a full wave rectified 230 volt RMS, okay, sine wave of 50 Hertz. So when you rectify a full wave sinusoid, so full wave rectification, when you do full wave rectification, the frequency doubles, and subsequently the value of the capital T becomes 1 by 200, and we have this expression, right? So that is going to be the discussion, major discussion in today's class. So please let me know if you have any confusion regarding anything so far. Because I'm going to end with a question here for you. Okay. So please let me know in the meantime if you have any question regarding anything that we discussed so far. So I'm going to ask you this. So this is the question. Find the Fourier series for this signal. And again, deriving it mathematically would be the challenging task. Other than that, rest would be pretty easy, I think. I believe personally. So if you have any question, please ask. So this amplitude is 5, this peak amplitude is 5, and this is 1. So 0, 1, so this is -1, this is 2, right? This is a signal. So your question would be, again, this is an even signal, okay? Try to figure that out. Okay, of course it's an even signal. So I would not have, for this signal, I would not have Bn components, right? I would not have sinusoidal components. I would have probably A0 and Ans, right? So question is, find the Fourier series for the signal. So that will be your homework. Again, you have to be able to mathematically express this, and also just so that you can actually solve this without any problem. This is going to be the year period span here. We have to take the signal from this point minus 0.5 to plus 0.5, because that constitutes one period about the origin, right? One full period about the origin. So because the period of the signal is 1, so you have to deal with from this. So you have to understand that. So those are the hints. This signal won't have any bn's, and this is the portion of the signal we have to deal with. So please try solving this, because this is going to be an easy one. Solving this and send me the answer as a homework. So with that said, we are going to end our discussion today. I will be here for 5 more minutes. Please let me know if you have any question. Okay, we shall be discussing convolution in the next class. Again, this class was entirely an workout. Okay, really like physical workout. This was a mental workout for all of us. So yes, I know working out is difficult, right? So again, please ask any question you might have, and also you can get in touch with me via email. If you have any query, please send me an email, and I will definitely answer your question. Anyway, so on the next day we shall be probably on Monday or Wednesday. We shall discuss about convolution, and then we shall jump into Fourier transform. As actually that is how things relate in our curriculum, right? So I would expect this problem be solved by you, because you will be able to solve this problem by now, I believe, because you shall have to mathematically describe the signal within that bound and then do the Fourier series, okay, based on that time period, right? And again, if you have any query, feel free to ask. Drop me an email. I'll definitely answer your questions, right? So, right, thank you very much. So we shall end our discussion today here at this point. I hope everything went well, although we had some intermittent network issues and solving so many things was quite challenging. I'll send you the handouts anyway. So thank you very much. If you don't have any questions, we shall end our discussion right now. Well, thank you to all of you. Thank you very much.